All right, so let's start this new section on 6.3, which is volumes by cylindrical shells. And so this is doing the same thing that we were doing in the last section, 6.2. But sometimes, as we'll see with this first example, the methods that we learned in that section don't necessarily work for every type of problem, which it comes up a lot in math. Some methods work for some problems and not for others. So that's what we're encountering here. So if we look at this problem, we could have seen a problem like this in 6.2. So find the volume of the solid. We're rotating around the y-axis, and we're bounded by y equals 2x squared minus x cubed, and y equals 0. So here's our region that we are finding the volume of once we rotate around the y-axis. Now, the problem is when we did a problem like this in the last section, we would find the outer radius, which would be from the axis of rotation to the outer part of the function, and then subtract the inner part of the function and integrate, and there we go. We get the volume. But now, if we wanted to do this, remember, if we're rotating around the y-axis using the washer method, we need to solve this equation for x and integrate in terms of y. But how do we do this? How do we solve? So we need to solve this equation for x, but that is not very easy. So some equations, it's hard to solve for a variable, and this is one of those. So we need a new method. So that method is called the method of cylindrical shells. So we can see from this figure here, we have a cylinder. We have it's hollowed out in the middle. If we take the radius from the center to this inner wall, we get R1, and then from the center to the outer wall, we get R2. The difference between those we're going to call delta Y. And then, of course, we have the height. So if we want to find the volume of this cylindrical shell, we can find the volume of the outer shell and then subtract the volume of the inner shell. So we'll call the outer volume, or the outer cylinder V2, inner cylinder V1. We're going to subtract V2 minus V1. So if you remember from geometry, maybe you saw this last semester in Calculus 1 as well, the volume of a cylinder is pi r squared times h. So we have pi, the radius of the outer cylinder is R2 squared times h, minus pi, radius of the inner cylinder is R1 squared times h. And we're going to do a little bit of manipulation on this. So we can factor out a pi, we can factor out an h. So let's write this as pi R2 squared minus R1 squared times h. Now this, of course, is the difference of squares. So let's factor that. Pi times R2 plus R1 times R2 minus R1 times h. And then we're going to do a little trick here where we multiply the top of this by the by 2 and then divide by 2. So we're not changing anything. We're just rewriting this in a new way. So we get 2 pi R2 plus R1 over 2 times R2 minus R1 times h. And so what we have here, we're going to call this R. So that's the average of the inner radius and the outer radius. That puts us right in the middle of that shell as far as the radius goes. So look up here again. We can see R is going from the center to the middle of the shell. And so that'd be the average of the inner radius and outer radius. Then we have R2 minus R1. That would give us the width of that shell times the height. And so you could think of this formula as 2 pi r, which is the circumference, times the height, times the thickness of that shell. Okay, so let's see what's going on here as far as finding the volume of these solids that we're looking at. So we have some region here, and we're going to rotate this around the y-axis. So here's what the eventual solid looks like. And we're going to do the technique, if you remember from Calculus 1, where you have, some curve like this, and you break it up into parts, and you find the volume at each of these parts, and then as you take that limit of the width or take the number of rectangles in that area up to infinity, you get the integral. And so that gives you the area. Doing the same thing here. So we have this cylinder. The height is dictated by the curve. The width is just however wide you want to make your shell. And then however many you end up with, that will give you a certain number of cylinders. You can find the volume of each of these cylinders, and that will give you an approximation for the volume of this solid. And then once you take that limit to infinity, of course, that gives you the exact volume. And so that's what we're doing. And so we end up with this integral from a to b. We have 2 pi x is representing the radius, and then f of x dx. All right. So let's look at this. We'll go back to this problem. This is actually example 1. But we're going to work it out this time using this method of cylindrical shells. So we don't really need to draw this one again. Don't need to draw it at all, really, because we only have one curve, so we know what's going on here. We do need to figure out what the limits of integration are. So you can probably go back up to the picture. I don't remember if it has it labeled or not. But we can just set this equal to 0 and solve for x. So let's factor out the x squared. And so we end up with x equals 0 and x equals 2. All right, so our integral is from 0 to 2, x times f of x, so 2x squared minus x cubed dx. So let's multiply out this x. So we get 2x cubed minus x to the 4th dx. And so then we'll integrate. We get 1/2 x to the 4th minus 1/5 x to the 5th from 0 to 2. And plug those in. 2 to the 4th, 16, divided by 2 is 8. And then 2 to the 5th is 32 over 5. And I believe when we work that out, we get 16 pi over 5. Okay, so again, like the last section, the integration is probably not a big deal. It's more getting it set up. And I think these are probably easier to set up. We're really just x times the function, and so that's not a big deal at all. And if it's, like the washer method, you might have one where you have one function minus another function, but not a big deal. All right, so let's look at this one. So we have y equals x squared and y equals 2x, rotating around the line x equals -1. So this is not an axis, so we're shifted a little bit. So I'll have to take that into account. So we have y equals x squared, and y equals 2x is going to look something like this. And so there's our region. And so we're rotating around that line there. So x equals -1. Okay, so v equals 2 pi. Now we need to figure out what our limits of integration. So we'll set, we need to figure out where these two intersect. Obviously that's 0. Now where is that one? So x squared equals 2x. Subtract the 2x. And factor out an x, and we get x equals 0, which we knew, and then x equals 2. So we're integrating from 0 to 2. Now this part's where it's a little bit different. We need to figure out what, so normally this would be x. We're 1 unit farther away from where we would be if we were on the y-axis. So now not x, but x plus 1. So we're subtracting x minus whatever that axis is. X minus -1 in this case. And then times, actually, I guess it'd be 2x. So we're going to, so our slice is like this. So the top function is 2x. The bottom function is x squared. And there we go. So now we need to FOIL this out. So FOIL, we get 2x squared minus x cubed plus 2x minus x squared. dx. And we can combine our like terms before we integrate. So we get 2x squared minus x squared. So that's x squared minus x cubed plus 2x. And so now let's integrate. We get 1/3 x cubed minus 1/4 x to the fourth plus x squared. And then, not dx. So 0 to 2. Then plug in our limits of integration. So we get 8/3, 16/4, which should be 4, plus 4. And then, of course, all those are 0. So we get those cancel out. We get 8/3 times 2 pi, which is 16 pi over 3. There you go. All right. So doing similar things, just kind of different formula, different way to think about it here. The cross sections always are parallel to the axis of rotation. With the methods in the last section, they were perpendicular. So you got to keep that in mind. And I would say practice is enough. I mean, with anything, practice is enough so that you're quickly getting them set up. Because once you get it set up, it's very easy.